about the small things, so. Forget about the big things, so. Say make we talk about the small things, so yeah.
Hello, my people out there. This is Edu Radio, your talk magazine program where they committed to inform you and enlighten you on waiting education don't carry, or waiting people when they manage education for Nigeria don't carry our education they see, and waiting me and you they observe. Education, when me and you know, now something when we say it they bring a lot of things to bear. It they break poverty to a reasonable extent. It they bring people to the fore to meet up with the challenges. It they make people, we be saying they rise, enable them to rise from their socio-economic stage, from one stage to the other. It they give you opportunity to interact. It they give you opportunity to prospect. It they give you opportunity to explore. It they give you so many things, even what they call swag. You know, go they timid. Education the key, Abi. Today, I be your team leader, your anchorman, Wimby, Oman, Dave. I don't give up. We still get our teachers, so this is supposed to be when we go to rest for our houses due to the pandemic when they declare as our children in the house. We can't change our own program. Make we bring this thing because of our public children. Because of our children when they wait for public schools. For Edu Radio, here be the only place where you fit get opportunity, especially children when no fit or parents no fit buy data. Enter, say then go subscribe for either DSTV, for their phone, or all of that to get online teaching. For here, we they give you. If you fit afford here, fine. But if you no fit, meet us every Tuesday, 4:30 to 5 o'clock. For Love 104.5, when they call Love FM, go get them. Today, our physics teacher, Ide Gidigba, to give you lecture. Today, no be physics, now chemistry, so enjoy yourself. As they come back, teacher, over to you.
Hi, listeners and viewers. Welcome once again to Edu Radio Nigeria. We are here to give you another piece of an episode in chemistry. I am by name Bisala Vincent Tanko, and you just sit back, relax, and listen as we learn together. Now, in case of feedback or you want to ask us questions, do endeavor to reach us through our handles, which are Facebook, Gmail, our website, address, and even on Instagram. So we are commencing right away. Today we are going to be looking at a topic known as chemical equilibrium. Chemical equilibrium. Well, a lot of students over time do ask this question: how do they know where the equilibrium of a system will be, that this a reaction will be, this and that, and it keeps giving them headache. But today we are going to be treating that as soon as we can and to make sure we hit it right on point. Now, when they say chemical equilibrium, generally reduction, what does that mean? You know, equilibrium generally we say, okay, when there is no change in something, when something remains stable, even though an external factor happen to affect it a bit, it still remain in equilibrium, remain without change. When there is an external force, an external factor that comes on or hits the system or touch the system in one way or the other, everything remains intact without any change. Any observable change is not found. That simply means the whole thing is in equilibrium. Now, what about chemical equilibrium? Chemical equilibrium, when a system in this context is known as a chemical reaction, okay? So, when we have a system that does not have any observable change, irrespective of any factor that is acting on the system, When there is no observable change on a system with time, that system is said to be in equilibrium. That is, that chemical reaction is said to be in equilibrium. Now, there is a scientist that brought about all these equilibrium, chemical equilibrium thing. It is known as Le Chateliers. Le Chatelier. Le Chatelier. Le Chatelier brought a principle which helps in this description of chemical reaction. Now, chemical equilibrium occurs in a particular type of system, which is a reversible system. A reversible system. A reversible system. This principle holds for a reversible system, like I've vividly said. Now, what is a reversible system? A reversible system is a kind of system or a kind of reaction. When I say system, you should know I'm talking about a reaction, a chemical reaction. So, a reversible system is a chemical reaction or a system in which there is a proceeding both forward and backward. When the system proceeds both forward and backward, then that system is said to be in equilibrium. It is represented by an arrow facing forward, an arrow also pointing backward. Like, for example, maybe we have reactant A plus reactant B that would give us a product C. You see this kind of arrow. Sometimes you might see a full arrow, like a headed arrow, full double-headed arrow like this. Sometimes it might just be a single one like that. And then this tells you immediately that you are dealing with a reversible system. Now, what is Le Chatelier's principle? That is what we're talking about. Le Chatelier's principle. Now, in this principle, it's just describing that when factors like temperature, concentration, or pressure happen to be changed in a system, the equilibrium system will decide to shift in order to nullify this change. Now, this that I've just said occurs in that is reversible. Most of the times we can say isolated system. Now, Le Chatelier's principle in a system, the system's equilibrium will decide to shift in order to annul or nullify this effect or these changes in the system. That is Le Chatelier's principle, like I've said. Now, also, we will also consider the effect of a catalyst. A catalyst. We also check the effect of a noble gas. Noble gas. The effect of a noble gas in a system. Now, considering all this, these are very important parameters that are used in describing the concept of chemical equilibrium. And as we pick them one by one to try to check the effects of temperature on a system, when there's a change in temperature on a reversible system, what will happen? When there's a change in pressure, what will happen? When there's a change in concentration, what will happen? What will happen if a catalyst is used? What will happen if a noble gas is used as well? So I would describe this immediately. So now let's look at temperature. Effect of temperature. Temperature effect or effect of temperature. Effect of temperature. System, for example, A plus B, that should give us a product C. Looking at this example, even though I'm going to give you a real chemical system for that, I'm using A and B to represent reactants and products here. So we should recall that when we say temperature, we simply means heat. Heat is involved in this kind of reaction. Now, we should consider exothermic and endothermic reaction. You should recall that. You should recall that. For exothermic, endothermic, we should all consider these factors. Now, exothermic reaction has to do with a reaction in which heat is given off in the environment, which makes the enthalpy change, or delta H, negative. while endothermic is a kind of reaction in which heat is absorbed into the system, which makes delta H, which is enthalpy change, positive. Now, what we are saying is, in exothermic reaction, when we have, for example, let me use calcium trioxocarbonate, for example, that dissociates to give us this. This is solid, this is solid, this is a gas. Now, let me assume that this system is exothermic, meaning delta H is negative. In an exothermic system, it simply means that heat is captured in the product side, and therefore an increase in the above system, an increase in the above system, an increase in the above system will make the equilibrium of this system to shift to the right, to the left, I beg your pardon, will make the equilibrium to shift to the left. Why? Because heat is already in existence at the product side. That is, the reaction will favor a backward reaction. So the reaction will favor backward reaction. In the above system, an increase in temperature, an increase in the temperature, let's say in the temperature of the above system, an increase in temperature of the above system will favor backward reaction. Exothermic is what we are considering, like I've said, and in this reaction, assuming it is exothermic, that is, heat is at the product side. By the time you increase temperature in this system, there is more heat already in the product side, which means the equilibrium will have to shift to the reactant side, which is the left-hand side, backward reaction, so as to nullify that effect, to balance up this too much heat that is at the product side. Whereas a decrease in temperature will favor the forward reaction. Why? Because heat is required at the product side, at the forward reaction, and now you are decreasing the heat or the temperature of the system. That means the heat at the product side will have to be reducing, and will therefore make the equilibrium to shift to the product side or the right hand side. So equilibrium will shift to the right when temperature is decreased in an exothermic reaction, and will shift to the left when temperature is increased in an exothermic reaction. Now quickly, let us consider an endothermic reaction. It is just a converse statement here. Now for an endothermic reaction, endothermic reaction, assuming this same system we have there is endothermic, meaning delta H is positive. In this same system, I'm using that as a reference too. If this system is endothermic, it is simple. By the time you increase temperature, increase in temperature will favor the forward reaction. The forward reaction. Why? In endothermic, heat is always absorbed into the system, meaning the heat is dwelling in the reactant side. Now, by the time you try to increase heat, there will be too much heat at the reactant side. Therefore, the equilibrium needs to shift to the product side in order to nullify this effect. While decrease in temperature will favor the backward reaction. Will favor the backward reaction. Now you can see what just happened here. When you increase heat in an exothermic reaction, the equilibrium will shift to the reactant side, that is to favor the backward reaction. While when you decrease, it will shift to the product side, favoring the forward reaction. Now, by the time you increase temperature in an endothermic reaction, it will favor the forward reaction. While if you decrease temperature in an endothermic reaction, rather, it will favor the backward reaction in order to nullify these effects. I believe this is quite clear. Effect of temperature on the equilibrium of a reversible system. Now, let us see quickly effects of pressure. Let us see quickly effect of pressure. Effect of pressure. This is always in gases. So let me use this for example. Sorry, N2O4 to give you yes, to give you this. These are all gases. This is dinitrogen 4 oxide, and then nitrogen 4 oxide, and then nitrogen 2 oxide. Now, if you have this, for example, as a system, all right, if you have this, for example, as a system, you increasing, now you should remember that pressure is inversely proportional to volume, but it is directly proportional to temperature. Now, if you have this and you are asked to give what